we are starting to get to the end of our one-dimensional NMR. So today what we're going to do, we've got a couple of more just problems to work out or work through. And then I'm going to talk about a couple of other techniques. And I mentioned these last time, so they are selective. Oh, that's not even where I wanted to put that, though. Down here, selective decoupling and NOE difference spectra. Okay. And then if we make it through those today, then we'll start into C13. All right. So any other questions or anything? Figured out those coupling patterns?
Overthinking way too much.
Mm-hmm. All right. So let's just start out by looking at another spectrum here. So C8H8O3.
What's benzene ring?
Yeah.
4 signals, so there's 2.
Right, so these
2 substituents.
benzene di-substituted.
And that's all the degrees of unsaturation. So there's
Is it?
right. There's only 4. Wait, no. There's. Wait, I'm mathing right now. Yeah, it's 4.
Unsaturations equal 8 minus 8 halves plus 1.
Yeah.
5.
But that's pretty helpful.
So there's 1 in addition to the benzene ring. Okay, so we started talking about the benzene disubstituted. So we have, essentially, if it's disubstituted, we have 3 different possibilities of substitution pattern, right?
Mm-hmm.
We can have 1,2 or ortho disubstituted. We can have 1,3 disubstituted, or we could have 1,4.
1,
1,3?
3.
How are you?
You have 2 doublets, a triplet, and a singlet as the main stuff. I mean,
Right.
obviously there's
Mm-hmm.
some crazy coupling inside it, but
And so which would be which here?
so the singlet's like a little bit below 2300.
Right? And
That's
which
the one that's by itself.
by itself. And then the big triplet is going to be this one, right? And then the other 2 are going to be one side or the other, depending upon what those groups are, right? So we have some X and Y attached on here. Okay, so what are the X and Y groups? Well, we could say, okay, so we've used up already C6H4. So we have, if we subtract that, we have C2H4O3 left over to attach. I'll put this down here. And I'm going to put one group here, one group over here. What?
No, I mean, oh, there's the methyl.
There's this proton here.
Oh, I didn't even see that. Yeah, okay, so it's...
Yeah, so
a
what
big
this
carboxyl.
means, right, is that it it's just downfield, and for them to show the whole spectrum, it would just spread it out so much. Everything would be so small. So they stick it up above, and it says that times 32, so they increased the size of it because it was very small and broad. You know, so it integrates for one proton, but it's just very broad. And so you were saying,
Carboxylic acid.
yeah, likely a carboxylic acid then.
Is it because it has low integration, or just because it's so downfield?
Because it's so downfield and because it's so broad.
Okay.
Right, because those carboxylic acids will tend to hydrogen bond and exchange a lot, right? Because they're acidic. And so they broaden out like that. So if we put a carboxylic acid on one side, what do we have left?
Methoxy.
A methoxy group. And do we have a proton signal for the methoxy group?
A little bit less than 4.
Yeah, right here. And this one is here. All right, so we know that this one in the middle is mostly the singlet. The one over here is the big triplet. So which is which for these other signals?
The right proton underneath the methoxy group would be the far left doublet, right?
The far left one? Why?
Because the oxygen's pulling electron density away from it.
Is that what we said that oxygens do when they're attached to the ring? Remember that this oxygen has non-bonding electrons.
Oh, so it's part of the system.
So it's going to, in resonance, so resonance is what it's going to do the most. It would have a, shift downfield if we were looking at the carbon spectrum of the carbon that's directly attached. So this would be kind of like an inductive effect here. But because the oxygen here has non-bonding electrons, it acts more. Let's see here, what am I doing? So it's going to donate electrons in here, and I have my bonds. I guess I can push them all the way around. And it's going to build up a delta minus over here, right? In this case, it's a little bit interesting because we have this methoxy group and we have the carboxylic acid, and the carboxylic acid is going to do just the opposite thing, right? So it's going to pull electron density up this way, and so it's going to pull it out of the ring. But these effects that it has, it's going to do this at the ortho position and at the para position, right? So, for example, this position here is ortho to the methoxy group, which should shift it upfield, but it's para to the carboxylic acid, which is going to try to shift it downfield. But I think it's true that perhaps the ones that are closer even here end up having a slightly larger effect. So I think you're probably right that this one is the more upfield one, and then this one here would be the more downfield, right? So this proton would be here, and this one would be here, right? And notice all these small couplings. So if we look at this one, it essentially has one large coupling, right, which would be the ortho coupling, and then it has two small ones, so it's a doublet of doublets. And the small ones are these meta couplings from here to here and from here to over to here, right? Same with this one, but it just happens that the two small couplings, the two meta couplings, are essentially the same size. So it makes it look like two triplets instead of, two more doublets. And then this one, right over here, just has the two meta couplings. So these two meta couplings would, match over here and match the ones over there. All right?
Then that triplet would be a doublet of doublets, but it looked like a triplet.
Right.
Okay.
Right. Well, it just turns out that for this proton here, the coupling to this side and the coupling to this side are essentially the same. Yeah, exactly. All right. So I think that there is a possibility for this. It wouldn't be 100% that this methyl group could be over here, right? Because phenols can be kind of downfield too and broad, but I think usually they're not this far downfield unless there's some hydrogen bonding to them or something like that. So yeah, I think that this is the better choice. All right, we got one more.
Unsaturated.
2 degrees. Everybody agree? Okay.
2.2 looks like a triplet of doublets.
Yeah, it does. A triplet of doublet or doublet of triplets or whichever way we want to say it. This one is a small triplet. So what about the integrations?
The triplet of doublets has 2.
Right, this is 2,
Triplets
1,
Then broad group.
4,
And 2 on the bottom.
if this is here,
Yeah.
2 over here, and 1 right here. Does that add up to what we need? 2, 3, 4, 5, 6, 10.
I don't like that it's 4.
Hmm?
I don't like that it's 4.
You don't?
Not particularly.
Well, this one here,
Well, like, I agree that it is 4, but like, it makes it a little bit more difficult.
well, I think what it means is that it's just 2 CH2 groups that are overlapping. And because it's so symmetrical, it could be that there's 2 CH2 groups that are strongly coupled to each other, and so they're second order, but coupling to each other.
That makes sense.
Right. Because it does look quite symmetrical, right?
It does.
So I think that's probably what makes it look like that. So this should be a CH2 and a CH2, like this. And because it's at 1.6, it's going to be, it doesn't have anything very strong, electronegative or anything else next to it. So we have 1 oxygen. What do you think is the functional group?
Ketone.
Yeah.
Because there's no broad singlet. I guess the 2.4 is broad singlet.
Well,
The hydrogen.
Whoa.
yeah.
Wouldn't it be no? Because there's only 1 proton there.
Aldehyde maybe.
No, you would see a signal at 10. And alcohol.
Oh, alcohol?
Yeah, because I just don't like calling it an alcohol. Because if that's the case, it would be that triplet between 2 and 1.8. If it were in chloroform.
It could be an alcohol next to a double bond. It's shielding it.
Well, there's no protons on the double bond if there is a double bond, right? Because they would be down at 5 or above. So if there's an alcohol and if we're seeing, we have to be, if there's an alcohol, we are seeing the alcohol proton, right? Because we accounted for all of the protons. So which one do you think it would be?
It would probably be the one more downfield. 2.4.
This one here,
Yeah.
probably. Less coupling, less structure to it, right? So let's just say that. So this is an OH. Okay, so we're not using the oxygen to make any unsaturation, right? We have 2 unsaturations. How can we make 2 unsaturations with a small molecule like this?
Branching.
Well, branching doesn't make unsaturations. It's just rings, right? Or pi bonds.
So it would have to be a ring.
2 rings.
Well, with 6, right, what could we do with 2 rings?
I mean, it's, that's probably more likely.
Yeah.
Is there another way to make 2 unsaturations?
Underring on the side ring.
Hmm?
Underring the right one.
Mm-hmm.
And,
Well, that one already has 2 unsaturations, right? So I guess if it was a bicyclic ring like this, then we'd have to figure out, where on it the OH would go, and then figure out how all these, couplings would fit in, and how we have 2 of the, this CH2 group. There's another way, though, that we can come up with 2 unsaturations.
Triple bond?
Triple bond.
Yeah.
Okay, so if we have this CH2, and notice that these 2 protons have this small coupling to each other. Right, this small coupling here, the doublet part of this, and matches this 1 proton over here. So this 1 proton over here ends up being, oops, dang. What am I doing? That one. The carbon on the proton on the end. And then we have another CH2 in here. So this is this proton. This are these protons. And there's this coupling here from here to here. It's kind of like an allylic coupling, but because it's on a triple bond, it's called a propargylic coupling. Okay, and so that's why that coupling is so small, too. All right, so what else do we have left over then?
oxygen.
Hmm?
Oxygen.
The oxygen. And
1, 2, 3, 4, 5.
One more carbon.
one more CH2, right? We have this one out at 3.6. Right, so we can go CH2, OH. Right, so these 2 are essentially together there. This one is down here next to the oxygen.
So there's 2 CH2 groups for the multiplet that's going on there?
Mm-hmm. What about them?
Is it just because their neighbor groups exist that it's so messy in the middle?
I think the reason they're so messy in the middle, so each one of those, if the couplings were roughly the same, then we would have, essentially n would be 4, and so then we'd have 5 peaks, right? So a pentet. However, we have 2 pentets that are right next to each other, and they're strongly coupling to each other. So they become very second order. So out of those pentets, the outside peaks have gotten very small, and the inside one's gotten big. And we saw from second order coupling that sometimes we end up with extra signals too. So let's see if we can, I wonder if that, do we still have this website open? Let's see if we could, oops, wake that
I guess I'm mostly confused by which protons are involved in that proton signal. Is it just the four, or is it
The which ones?
the?
In that signal, so there's all four of those protons that are buried together in there. Does this have?
The second, like, suggested one underneath the search.
Oh, right here. Good. I was gonna look for like some kind of history. Oh, that's not what I want. Let's go out and do our NMR simulator. Okay, so we're gonna say we have 2 and 2, and our signals, let's move them a little bit farther apart first. So say 1.7 and 1.5. So I'm going to put these two at 1.7, 1.7. Oh, I guess well, let's do the 1.5 first. I don't know if it matters. 5, 1.7, 1.7, and these are going to be zeros. Okay. All right, and then 1 and 2 are not going to couple with each other, but 3 and 4 will couple with 1 and 2. So let me see if I can remember how to do this. 4 goes to 1. Let's say at 7 hertz, we'll use a standard 1. 1 and 2, both at 7. 1 and 2, both at 7. Okay, so if we have CH2 and CH2, and if they're first order, then, is that right? No, I think we gotta take into account more than that, don't we? CH2, each of them are gonna have another CH2. So, we have another CH2 at 2.2. I think we can fit it all in here. 2.2.
Okay, so overall it represents a chain of 4, but we're looking in the middle too for those.
Yes, exactly. And so those aren't going to go to there. These two are going to go out here. We'll just keep the couplings the same. Okay, and then we're going to have one more CH2. Okay, I'm going now. I can't stop. 3.6. And these are going to couple to 3 and 4, 1 and 2, right? Because these are the 3 and 4. They're on the is on the opposite end of the chain.
Yep.
Okay, so let's look at this. All right, so like we said, that these two here in the middle should be essentially pentets or quintets or whatever they call them, right? So I think the complication will arise when we bring these two closer and closer together. See, because they're mostly first order here, though we see these, the inside peak is just slightly higher than the outside one, right? But if we bring these closer, let's say go to 1.6 and 1.6, they're going to start to get, they're mostly pentets, 1, 2, 3, the same, but they're starting to get a little bit of extra splitting. Let's go 1.65, 1.65. But they start to get very second order then, right? And does that almost looks like that. Let's go just a little bit closer, like 1.67. You know, and it starts to look reasonably close to that, right? So yeah, it's just those two in the middle, which if they were far apart in chemical shift, would just look like these two quintets, but as they come together, they're just second order on top of each other. Well, that was fun.
Answer my question.
All right. So let's just talk a few other little details. We talked about this, kind of alluded to this a little bit the other day. But, you know, if you've been doing NMR in the lab, then, you know some of this. But, you know, it may be, too, that you're just used to using one NMR solvent and you don't vary them much. So there are a bunch of different NMR solvents that we can choose, and some, things that we need to consider when we choose an NMR solvent is, of course, the solubility of your compound in the solvent. It needs to be a deuterated solvent, at least some of it. I was talking with Steve, and he said sometimes now what they're doing is just using a small amount of deuterated solvent in regular protonated solvent, and then he does it's called a solvent suppression.
Yeah, but if you've looked at the spectra that he
Yeah. I think the only place that you could do that very well is if that solvent peak is well resolved from any of your other peaks that you want to look at. So usually we want to have it deuterated, and you can get different kind of percentages of deuteration. So the highest, you can get what they call 100% deuterated. Which still isn't quite 100%. There's still a small amount of protonated solvent. But you only really need that, too, if you have very small amounts of sample. Usually, they're 99.9 or something like that. Availability, of course, we need to be able to buy them. Cost, maybe, unless your boss has big bucks. Just burn through whatever most expensive solvents, and peak dispersion. So like we were talking about the other day, peaks can move around in different solvents, right? So sometimes you just have to do a trial and error. So this is just a small part of a table in our text, Appendix H. And what it shows is different NMR solvents across here. And it shows where the residual solvent peak, so the proton in the residual protonated solvent would be here. So if it's deuterial chloroform, then if it's chloroform in deuterated chloroform, then it's at 7.26. Okay. What it doesn't tell, and I'm surprised about this, is for all of these, most of the other ones, the solvent peak is going to be some kind of a multiplet, right? Because if your deuterated signal, well, except for benzene, I guess. In any of these others, let's take acetonitrile. Usually, the actual protonated peaks that you would see would be something like CH2D CN, right? And so, no, CHD2. Like this. All right, and so you'd be observing this H and oftentimes referencing your spectrum to that signal. But this proton will be coupling to the deuterium atoms. And the thing that complicates this is deuterium has a spin of 1. And remember, we used this n+1 rule, but what we said was that, oops, why wasn't that right? Was that really it was, what was it? It was 2I n plus 1, right? So if this I is 1, then it's 2 times 1 is 2 times 1, if we only have one proton next to it, plus 1, and so we get 3. So for every deuteron coupling to a proton, it's going to split that proton into 3 peaks. Right? And we see this, to jump ahead a little bit, do you know what, when you're running C13 NMR, what the chloroform peak looks like? Is 3 peaks, right? Because we have C, D, Cl, 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 and so this peak has 3 in a 1-to-1-to-1 ratio because it's being split by the deuterium because it has a spin of 1. So all of these have, more complicated, patterns and stuff. But so the other interesting thing or important things, and we alluded to this the other day too, is this also shows where if you have residual water in your sample, so if it's wet, where that peak will be. So in chloroform, it's just over 1.5. We were talking about that. But notice in different solvents, so DMSO 2.8, no, that's acetone 2.8, in DMSO up by 3.3. And I think one of the interesting ones is if you do it in benzene, it moves that water peak all the way up to 0.4. So, for example, if you were using chloroform and you didn't have much sample and your water peak was at 1.5 and it was right on top of a bunch of signals that you wanted to look at, you could switch to benzene and it'll have some other effects on your spectrum, but it'll move the water peak all the way up to 0.4, which will usually just be out of the way of everything else. So then there's some other solvents there too. But what it also does, and this table is long, is it also has chemical shifts for some common impurities that you might have in your sample, right? So if you have some dichloromethane that you didn't get pumped all the way off from your extractions or something, it tells, if we could actually see that, it tells where those peaks should be in the different NMR solvents. And see, as you go across that line, it moves around a little bit depending upon what your NMR solvent is. Or diethyl ether, I chopped it off here, but here's the methyl group for diethyl ether, and the table's bigger, it has the CH2 group for the diethyl ether there too. And so, yeah, you can look at that and it shows where, those common impurities, ethyl acetate or, these kind of things that you might have in your NMR samples now and again.
Sometimes.
So I think it's kind of handy. All right, so we're going to start talking about some of these other techniques. Any other questions? No? Okay. All right, so this first method is a way that we can confirm which peaks or which protons are coupling to which other ones. Beyond just measuring the sizes of the coupling constants. Okay? So the first one is going to be a selective spinned coupling experiment. And so essentially what we do is we run our normal spectrum, but then we take a second radio frequency and we selectively apply it to one of the peaks in the spectrum. Okay? And so I guess if we could draw out what our pulse sequence would look like. Remember, we have if we're just looking at the proton spectrum, we'd have our pulse, we'd have our acquisition, and our delay, another pulse, acquisition, delay, right? We'd be repeating this. So this is our main proton channel. But what we would have is a second proton channel, let's say H2 channel, and the important part of this would be either that we would just keep it on all the time, or we would at least turn it on during the acquisition. So we're applying this radio frequency, and this is a selective just at one frequency or one narrow band of frequency. And we want to have it on while we're acquiring the signal. Okay. The rest of the other proton channel is like a broad band, so it covers all of the protons in the spectrum. Okay. So, kind of the idea of what happens here, right? If we have our system like we were talking about, where we have splitting, right? If we're observing this one here, the splitting comes from the fact that the adjacent proton can have two possible spins, aligned and opposed, and those are roughly in the same population, right? And so the one that's aligned with the magnetic field adds to that external magnetic field, and so half of our signal shifts to a higher frequency, the other part is opposed, it subtracts, shifts the other half, to a lower frequency, right? That's how we got like a doublet. So what we're going to do in this is we're going to apply this, let's say B1 to these spins right here. And I think there's a couple of different explanations. One is that what happens when we do that is that those spins just start flipping back and forth or going from one energy to another very rapidly, and much more rapidly than we can actually measure the spectrum. And so it essentially cancels out. All right, so it removes the splitting. So this has rapid spin flips, cancels the signal. So essentially removes the splitting to that proton. I think I read one time too, another way to think about it is that it equalizes the spin populations, so they're all in the XY plane, but there's no phase coherence, and so they're just random in that plane, and so if there's no plus and minus, then it can't couple to something next door. Okay, so when we irradiate this other signal, then it removes all coupling to that proton. Okay, so here's a spectrum. This was something that we did a long time ago when I was a young faculty member. And so here's the spectrum that is kind of the standard with no decoupler. Though technically what you would do for your reference spectrum is that you would apply this other radio frequency at some point in the spectrum that was not on a peak, because just having the decoupler on can tend to shift some things around a little bit. So your reference should be as similar to what your other experiments are. And so the best reference is having the decoupler on, but off resonance. Okay, so here's the spectrum that we have with essentially no decoupling. Okay, so we're going to kind of walk our way through this, and we're going to place the decoupler on different peaks. Okay, and when we do that, it's going to kind of just squash the peak that we're irradiating, and then we'll look at other parts of the spectrum and see how they've changed. Okay, so here's the reference in the bottom. And up here, we have irradiated another peak. So this says at 4.9, so the B1 has been put right on this peak at 4.9. Okay, so that peak is essentially gone. And then what we do is we look down the rest of the spectrum and we look for something that's changed. So what's changed?
Halfway, like 3-ish.
Like this one right here,
Yeah.
right? So this essentially went from a doublet to a singlet, more or less. So whether it has some stuff at the bottom, it always depends a little bit on whether you use the right amount of power and stuff on your decoupling, because you can partially decouple it and you'll see it change, but it may not remove that coupling constant completely. So if this went from doublet to singlet, it shows us that this doublet over here is arising from coupling with this proton over here. Okay? Otherwise, we just have to measure the size of those coupling constants and see if they match. But then what if that's a size of that coupling constant, matches one of the other peaks? Then it doesn't really confirm it. But this way it shows, for sure that proton, those two protons couple with each other. Okay? So the other thing you can do then, of course, is then to decouple the other coupling partner. All right, so here's our reference again. And this one we've decoupled here on that other peak that collapsed. And what we can see is that this one is mostly collapsed now as well. Right? And has anything else changed? Doesn't really look like it, right? So these two, we've confirmed that these two couple to each other.
And that they're alone, basically, right?
Right. Though this one is a triplet, so I guess this would be a CH2 then. And this would be a CH.
So for each one of these, you do 2 spectra? Kind of.
Well, we can the reference one, we can just do at the beginning.
Right.
But we just plotted them together each time. I just put them together each time so we can compare more easily.
Oh yeah, what I mean is use B1 on both suspected sites. Right?
Well, yeah, so we're just going to I think that's the most complete way to do it if you can, to show it goes one way and show the other. But then what we're going to do is we're just going to kind of walk down and hit every peak here. So we just went from the furthest one downfield. This is 2 methoxy groups here. So that one doesn't actually have any coupling. Okay, so now we've moved in and hit this one right here. And what looks like it's changed.
1.5-ish.
Yeah, this one right in here, right? It still has some coupling in there, but it's definitely changed, right? So we know that these two couple with each other. One thing that this helps as well is if you have, one of these patterns that's really complicated, and you can hit one of the coupling partners, then you'll simplify the spectrum, right? You remove one coupling, and you see what's left over, right? So it's like if we're drawing out one of those trees, and you just remove one of those, you'd have, all the couplings that are left. So it'd simplify the pattern. Okay, so then here, we've hit this one here. And I'd say that this peak again changes.
Yeah.
Right, so we know also that these couple to each other. And then this one's a little messy. We hit here. It's probably hitting these other peaks as well, but they look like singlets anyway. One of them, I don't know if they're both methyl groups or if one of them, I guess the upfield one could be water as well. But when we hit that, then notice that both of these collapse. Right, so essentially what we have is CH2, 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 right? One of them is over here, one of them is over here, and this one is in the middle. So it's not a very complicated system here, but we can just walk our way through, and if you only had a few of these to do, it's pretty easy to do. You know, we'll learn, you know, when we go on into 2D NMR, you can do like a cozy spectrum, and it tells all the same stuff here. Well, except it's harder to get the actual coupling constants.
That it is. Yes.
Okay, so the last experiment that we're going to talk about here, it tells us about through space interactions, so proximity rather than through bonds. Okay, and it's called the nuclear Overhauser effect. Sometimes it's written like N-O-E, because Overhauser is somebody's name, so that part of it is always capital. Okay, so what we do is we irradiate with a weaker signal, one signal, and that leads to relaxation. And when it relaxes, it can transfer some of its energy to protons that are in close proximity to it. So the pulse sequence here is going to look a little bit different than what that decoupling was. So here's just our normal proton pulse. I'll just call this 0. So we're going to do this selectively again. So it's kind of like the last one, though we're going to use a slightly lower power. And what we're going to do is we're going to turn on this decoupler. So this kind of is kind of like a switch on and off. So this is on, and then we're going to turn it off. So we don't want it on during acquisition. We're not trying to do decoupling, but we want to put some energy into a certain proton and then let that energy propagate to other signals that are in close proximity. And then we detect it. Okay, so we're going to turn it, it should be on here, on, off during acquisition, on, off, like this. Okay, and again, this is a selective irradiation. All right, so this works, experiment works mostly the way it's run here for small molecules, which means something like the molecular weight at least less than 1,000. Okay, because this NOE effect is dependent upon how the molecules tumble in solution. And if they tumble very rapidly, then this is what we get for small molecules. Okay, and we get what we call a positive NOE. But if you have very big molecules like proteins or something, they tumble very slowly and you get a negative NOE. And in fact, so then you could draw a line here. This is kind of proportional to mass, though it's really what they call the correlation time, and that has to do with how the tumbling. And over here would be the NOE, and this might be some 0 point here, but so what it does is the curve runs something like this, from positive down to negative. And so there's at some mass where this essentially goes through the 0 point, and so you wouldn't see any NOE. But for small molecules, we get this positive NOE, means that when the signal gets transferred to an adjacent or a proton in close proximity, it will make that peak bigger. Okay? A negative NOE means that it's going to subtract from it. It's going to make it smaller. Okay, so this has to do with, tumbling rate. All right, so the other thing about how we run this, and I don't know if I left myself hardly enough space, is because these effects are very small, maybe, it says here, less than 20% enhancement. And oftentimes smaller than that. So what we would do, if we're going to do this, is we usually run them as difference experiments. So what we do is we run a reference spectrum that, like we did that last time with the decoupler at some off-resonance position, so not on a peak. Then we record the on-resonance spectrum, and then we subtract the reference spectrum from the on-resonance spectrum. Okay, so we have like this. We have number one, let's do our reference. And so we're going to have, say we have 3 peaks like this. We're going to, and here's our radiation over here. So it's off resonance. Okay. Then we're going to do our experiment, and we are going to irradiate, let's say we irradiate this peak. And so like we saw before when we did decoupling, this peak essentially disappears, and these are like this. Okay? And it may be, well, let's say this one gets a little bit bigger. All right? But it's going to be hard if it just gets, 10% bigger or something. Your integration may not be good enough to see, oh, this one is 10% bigger and this one's not. And so what we do is we take our experimental one and we subtract our reference spectrum. And you can either do it as spectra, or oftentimes you subtract the FIDs and then you do the Fourier transform. But what you'll get if you took the experimental one and you subtract the reference, then you have like no peak here, and you subtract this one, so you end up with a negative peak where your irradiated peak was. And then you see some small peak, and this is just this is how much it increased, right? It got enhanced. And then if this one is not close by, that one would just be, canceled out, right? So we're just looking at what the difference between those two spectra. So in this case, if this one got enhanced, this is, the enhancement. And you can actually, if you do these really carefully, you can actually integrate this. It would give a negative integration like this, and then you'd have some small integration like this, and you can compare those, and you can see what percentage the enhancement peak is relative to this negative one, and you can give a percent enhancement. And people used to do this stuff, and you could use some standard molecule where you know roughly how close 2 protons are and see how much it gets enhanced, and then do that for your experimental one, and you could actually kind of measure a distance. But you have to be really careful. You know, you have to like degas the sample because oxygen in there will cause it to relax faster. You got to make sure there's no other things in it. You got to prepare it really carefully. And they used to always say that this, at least this was the story when I was doing these, that that any kind of things around, people walking around, getting close to the magnet or in the other room, or a big truck drives next to the building or anything, so these can influence the magnetic field strength. And then if it has some variation, then when you do the subtraction, it won't subtract correctly, right? Because if the magnetic field is not as homogeneous as you need it to. So whether that was so critical or not, but we used to come in to do these like late at night when there was nothing going on. All right, so here's some examples. So this is a molecule maybe you'll recognize from problem set. If you haven't done it yet, could give you all the answers already. So this is something that I worked on when I was a fresh postdoc, University of Utah. This compound came from a sea squirt, tunicate, marine tunicate. And so because all of these were relatively, well resolved, I decided just doing some selective decoupling would be almost as good as a cozy, though I have a cozy for it too. So what we're seeing here, this is a reference spectrum down here, and this is the difference spectrum up at the top. So here's the irradiation at this HA, and what we see is enhanced signals. Well, what we see is signals for B, D, and F, but notice that, for this peak here and this one here, those are gone, right? So we're learning that HA is close in proximity to these other three protons, okay? And in the structure here, here's HA, right? So we see it's close to HF, HD, and I actually measured these percents. So this is 10%. I don't know if you can you see that? 10%, 7%, and then to HB over here. Doesn't look close, but that, that bond can rotate here. There would be some hindrance because there's some conjugation there, but it can rotate some, which would put it up close to it. So I think here it would be not only distance, but some kind of population difference as well. Okay? So then, just like the other one, I can come through here and kind of do some of these separately. Here I've done HF, and I see HE and A. Notice that this one has some structure, but notice it has positive and negative, positive and negative. So if you integrated this thing, it kind of integrates to 0. So this is probably just a subtraction error, right? Just like this one has a negative and a positive, but this is actually the water peak, I think, which sometimes moves around a little bit, and so it doesn't subtract so well either. So we see from F to E and A, here's F, goes back to A, which we measured before, the opposite direction, and then F also goes out to G. But we don't see it to C. So, so this one maybe holds its shape more and doesn't rotate back around as much. Oh, this is a different compound. This is what I did in grad school. So this one, notice this is much noisier, so it was smaller amount of material. So in this one, I synthesized this compound here. And this has, so this has an H right here. And this had an aldehyde over here. So I did this through an intramolecular, I think this had something else over here, Diels-Alder reaction, okay? And so when this closes up, I could get two possible stereochemistries across this ring junction here. So I had to be able to tell the difference between the cis and the trans ring junctions. So I got both of two compounds, and I had to tell which one is which. Okay, so I used these NOE difference experiments, and in this case, let's see. This one is, this H is H6, this is H1, and this one is what's called H7. Okay, so I irradiated here was H6, this proton right here. And it's a little bit further downfield. You can, here's the full spectrum. So, they're kind of reasonably well resolved. And I saw some, they're not big, but some enhancement of H1. So that's going over here. And H7, which is going over here, right? So that tells me that, so the chiral centers here, where the isopropyl was and where this methyl group, those came from my starting material. So I knew actually the chirality of those. And so I knew that the isopropyl is back, so this H is up, and if I see an NOE between H6 and H7, that tells me that H6 is up as well. Just put them on the same side, and then I saw the enhancement of H1, so this spectrum, this compound here, was the cis ring junction. And I did this on the other compound. I didn't put a spectrum in here where it was trans, and I didn't see this NOE across here because when it's trans, they're far apart. All right? Okay. So that is kind of the end of what we're going to talk about, just our 1D and proton NMR. Okay? What time is it? We can just do a little bit intro to C13. Okay, so I'm going to stop this one.